Let's dive into the concept of force, a fundamental idea in physics. Force is a vector quantity, meaning it has both magnitude and direction. We measure it in newtons or dynes depending on the system. Force can start motion, stop it, speed things up, or change direction. It can even alter an object's shape or size. Simply put, force is what changes how things move or stay still. Let's talk about balanced and imbalanced forces. When the forces acting on an object add up to zero, we call them balanced forces. These forces can't start movement, the object stays still. Think of a tug of war where both teams pull equally. The rope doesn't move. On the other hand, if the forces don't cancel out, they're imbalanced. That's what sets things in motion. For example, when you push a bicycle, your force overcomes friction, and the bike moves because the forces don't balance out. Let's break down what a dyne and a newton really mean in terms of force. We start with the basic formula. Force equals mass times acceleration. If we take a mass of 1 gram and accelerate it at 1 centimeter per second squared, the force involved is 1 dyne. It's a tiny force, but it's a useful unit in the centimeter-gram-second system. Now, if we switch to 1 kilogram and accelerate it at 1 meter per second squared, that force is 1 newton. This is the standard unit of force in the metric system. Let's talk about rest and motion, two concepts that depend entirely on your point of view. An object might be moving compared to one thing, but standing still compared to another. Imagine you're on a bus. You're sitting still relative to the bus itself, but moving fast compared to the trees and houses outside. So, rest and motion aren't absolute, they're always relative. When something doesn't change position compared to its surroundings, it's at rest. When it does, it's in motion. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's talk about velocity, how fast something moves in a certain direction. When an object covers the same distance every second, its velocity is uniform. It's steady, predictable. But when the distance changes each second, that's non-uniform velocity. The speed isn't constant, it might speed up or slow down. Understanding this difference helps us describe motion more accurately, whether it's a car cruising down the road or a ball rolling to a stop. Let's talk about acceleration due to gravity, that constant pull that makes things fall toward the Earth. On our planet's surface, this acceleration is about 9.8 meters per second squared. Now, to understand motion under gravity, we use a set of variables: displacement, initial velocity, final velocity, acceleration, and time. These come together in what we call the equations of motion, formulas that connect all these factors and help us predict how objects move when gravity is involved. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's look at two examples involving vehicles starting from rest and accelerating. In the first, a vehicle accelerates at 0.5 meters per second squared for 4 minutes. We want to find its final velocity and the distance it covers. In the second, a car accelerates at 0.2 meters per second squared for 2 minutes. Here, we're asked to find the distance traveled. Remember, when something starts from rest, its initial velocity is 0. Also, if it comes to rest after moving, its final velocity is 0. And if it's slowing down, acceleration is negative. This slide presents a series of practical problems based on equations of motion. We're looking at scenarios like a girl running at a steady speed, a car accelerating north, and a bus braking to avoid a boy on the road. Each question challenges us to find acceleration, retardation, distance, or time using uniform motion principles. These examples help us connect theory to real-world situations, making the concepts of velocity, acceleration, and stopping distances much clearer and more tangible. Here, we see a series of numbers and values that seem to represent answers or results from a calculation or analysis. The key takeaway is the final statement: accidents do not just happen by chance. This suggests there's an underlying cause or pattern behind incidents, something we need to understand and address. It reminds us that safety and prevention require careful attention to the factors at play, not just luck. Let's talk about inertia, a fundamental concept in physics. Simply put, nothing can change its own position by itself. If an object is at rest, it wants to stay at rest. If it's moving, it wants to keep moving in the same direction at the same speed. Only an outside force can change that. This natural resistance to change is what we call inertia. It comes in two forms, inertia of rest and inertia of motion. Both describe how objects resist changes to their current state. Let's talk about two important types of inertia of motion and inertia of rest. Inertia of motion means that an object already moving wants to keep moving. For example, a fan keeps spinning for a while after you switch it off. Or when a bus stops suddenly, passengers lurch forward because their bodies want to keep moving. On the other hand, inertia of rest is about objects at rest wanting to stay still. Like when you shake a mango branch and the fruit falls, or when dust falls off clothes as you beat them. Both show how things resist changes in their state. Let's start by thinking about which object is harder to pull. Then, imagine pulling both the same distance and letting go, which one swings back and forth more times. Why do you think that happens? From these observations, we can draw some important conclusions. Finally, we'll look at an experiment that clearly shows how inertia depends on mass, a key concept in understanding motion and resistance to change. Let's look at what happens when we pull the cardboard slowly. In this case, the coin moves along with the cardboard, both going into motion together. But when we pull the cardboard very fast, something different happens. The cardboard moves quickly, but the coin stays still because of its inertia. It resists change in motion. As a result, the coin drops straight down into the glass. This simple experiment shows how inertia works in everyday life. Newton's first law of motion gives us a clear way to understand force. It tells us that an object will stay still or keep moving in a straight line at a steady speed, unless something else, an external force, acts on it. That's why force is defined as whatever changes an object's state, from rest to motion or the other way around. This law also explains inertia, the tendency of objects to resist changes in their motion. So, Newton's first law is often called the law of inertia, because it describes this natural resistance to change. Let's explore some everyday examples of inertia of rest, the tendency of objects to stay still unless acted on. Imagine a mango hanging on a branch. When we shake the branch, it moves, but the mango wants to stay put. So, it detaches and falls due to gravity. The same goes for dust on a carpet. Hitting the carpet moves it, but the dust resists motion and falls off. And when a bus suddenly starts moving, our lower body moves first, while the upper body lags behind, making us jerk backward. That's inertia in action. Let's talk about inertia of motion, a concept that explains why things keep moving even after the force stops. For example, when you turn off a fan, it doesn't stop immediately. That's inertia at work, keeping it spinning. An athlete uses this too, running first to build momentum before a long jump. And when a bus stops suddenly, our bodies jerk forward because the upper part keeps moving while the lower part stops. That's also why jumping from a moving bus is dangerous. Your body can't adjust quickly, and you risk falling. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Newton's second law of motion tells us how force and motion are connected. It says the rate at which momentum changes is directly tied to the force applied. In other words, the stronger the force, the faster the change. And importantly, this change always happens in the direction of the force. This law helps us understand how objects speed up, slow down, or change direction when pushed or pulled. It's a fundamental principle that shapes much of classical physics. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Here, we see a series of numerical problems focused on force and motion. They ask us to find acceleration, stopping time, and force based on different scenarios, like a body slowing down under a retarding force, or a vehicle braking to avoid an accident. Each question builds on the core concepts of Newton's laws, applying them to real-world situations. These answers help us check our understanding and see how the theory works in practice. Newton's third law tells us that every action has an equal and opposite reaction. But here's the catch. These forces don't cancel out because they act on different objects. Think about a rocket launch. The gases shoot down, pushing the rocket up. Or firing a gun, the bullet flies forward, and the gun kicks back. When we row a boat, water moves backward, and the boat moves forward. Even a balloon releases air downward and lifts upward. It's all about pairs of forces on separate bodies. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Thank you for joining me today. I hope you found the ideas we explored inspiring and useful. Remember, every step forward counts, and together we can make a real difference. I appreciate your time and attention. Let's keep the conversation going. Until next time, take care. This video was created with SlideSpeak. Visit SlideSpeak to turn your presentations into engaging AI-narrated videos.